Look up at the night sky and picture a star flaring brighter than Venus. In 1572, that exact event shattered humanity's understanding of the cosmos. This was the Tycho Supernova, a cosmic explosion that did more than just light up the heavens. It tore down a 2,000-year-old belief that the stars were perfect and unchanging, directly paving the way for the science of astronomy we know today. By the end of this journey, you will understand how one brilliant flash in the dark rewrote the rules of the universe. We will uncover the meticulous records of a Renaissance astronomer with a metal nose and reveal how the ghost of that same explosion is helping scientists today hunt for dark energy. What forgotten event from history do you think holds the key to our future? To understand the shock of that new star, you must first step into the mindset of a world governed not by telescopes and data, but by ancient philosophy. For nearly 2,000 years, Western civilization held one truth to be self-evident. The cosmos beyond the moon was a realm of perfect, immutable order. This was the universe according to Aristotle, a celestial machine where stars, fixed to crystalline spheres, moved in eternal, predictable harmony. This was not just a scientific idea, it was the bedrock of reality, woven into the fabric of religion, art, and power. The Earth, flawed and changeable, sat at the center of this divine arrangement, a stark contrast to the perfect heavens above. So when people looked up on an ordinary night in 1572, they were not just seeing points of light. They were observing a perfect, unchanging creation, a testament to a stable and orderly universe. The sudden appearance of a brilliant new star did not just break the silence of the night. It threatened to shatter the entire philosophical foundation of their world. Into this world of cosmic certainty stepped a man as brilliant as he was bizarre. Tycho Brahe was a Danish nobleman whose life was a tapestry of duels, royal patronage, and an insatiable hunger for celestial truth. After losing part of his nose in a youthful sword fight over a mathematical dispute, he famously wore a prosthetic made of silver and gold, a man literally rebuilt for his pursuit of knowledge. But his true masterpiece was not his metal nose. It was Rewrote, his island fortress of astronomy, a palace built not for war but for the stars. Here, on the island of Ven, Tycho constructed a scientific citadel funded by the King of Denmark. Rewrote was more than an observatory, it was a temple to precision, filled with the most advanced instruments the world had ever seen, all built before the invention of the telescope. Imagine giant brass quadrants the size of cathedral windows and intricate sextants that turned entire rooms into measuring devices. With these monumental tools, Tycho and his team of assistants could track the positions of stars and planets with an accuracy that was simply unheard of. He achieved a precision within one arcminute. To grasp what that means, picture holding a coin at arm's length. One arcminute is roughly the apparent size of a single ridge on that coin's edge. That is the breathtaking scale of his observational power. This meticulous, data-driven approach was his true revolution. So when that strange new star blazed into the constellation Cassiopeia in November 1572, Tycho was not just a man looking up. He was the one person on Earth equipped with the tools, the team, and the temperament to study it properly. While others saw a philosophical crisis, Tycho Brahe saw a data point, and he began his nightly vigil, measuring its position with a relentless, unwavering focus that would change everything. On a cold November evening in 1572, Tycho Brahe was walking back to his chambers after a long night of observation. He glanced up as he always did and froze. There, in the familiar W shape of the constellation Cassiopeia, shone a star that had no right to be there. It was not a faint smudge, but a piercing beacon of light, rivaling the planet Venus in its brilliance. This was November 11th, the night the old sky died. The new star was so intensely bright that within days, observers across Europe and as far away as China reported seeing it with their naked eyes in the middle of the day. a defiant pinprick of light challenging the very sun. For the average person, it was a miracle or an omen, a sign from God that filled them with awe and terror. For the scholars and astronomers clinging to the teachings of Aristotle, it was an intellectual catastrophe. How could a new star appear in the immutable heavens, the foundations of their world, built on 2 millennia of philosophical certainty, were cracking wide open with the silent, glaring light of a single, impossible star? That single point of light did more than just shine. It declared war on 2,000 years of established thought. For the astronomers and philosophers of the era, the new star presented an impossible puzzle. According to the unshakable teachings of Aristotle, the cosmos beyond the moon was composed of a perfect, incorruptible substance called the ether. This celestial realm was designed for eternal, circular motion, not for the messy, unpredictable acts of creation and destruction that defined the Earth. Stars were fixed, permanent fixtures. They did not simply ignite out of nowhere. The immediate reaction from many scholars was therefore one of denial. They argued it could not be a star at all. Perhaps it was a comet or some other atmospheric phenomenon lurking in the upper air, safely within the corruptible sublunar sphere where change was permitted. This was a desperate attempt to fit an impossible observation into a flawed but comfortable worldview. But Tycho Brahe, armed with his unprecedented data, had the evidence to dismantle this argument completely. Night after night, he tracked the object's position with his giant instruments. If the new star were a nearby comet, its position would shift slightly against the background of the true, fixed stars due to parallax, the same way your finger seems to move when you view it with one eye closed and then the other. Tycho's meticulous measurements revealed no such shift. The new star held its place among its celestial neighbors with an absolute rigidity. It was not in our atmosphere. It was not a local phenomenon. It was truly, undeniably out there in the realm of the stars. This was the death blow to the idea of immutable heavens. The cosmos was not a static painting on a crystal dome. It was a dynamic, living entity capable of change on a scale that dwarfed human imagination. The crack in Aristotle's perfect universe had become a chasm, and through it modern science would soon walk. Tycho's crucial insight was not just in observing the star, but in asking a simple, brilliant question. How far away is it? To answer this, he employed a classic method of measurement known as parallax. Think of it this way. Hold your thumb up in front of your face and close one eye, then switch and close the other. Your thumb appears to jump back and forth against the background. That apparent shift is parallax. The closer an object is to you, the larger the shift. Tycho applied this same principle to the new star, using the Earth itself as his second viewpoint. As our planet moved in its orbit, he reasoned, a nearby object like a comet should show a noticeable shift in position against the distant, fixed stars. Night after painstaking night, he recorded the star's precise location with his giant instruments. The result was a stunning absence of movement. The new star displayed no parallax whatsoever. It was not just beyond the moon. It was lodged deep within the realm of the so-called fixed stars, a place Aristotle had declared eternally unchanging. With that single, data-driven conclusion, Tycho did more than just chart a celestial object. He used empirical evidence to dismantle a 2,000-year-old pillar of natural philosophy. The heavens were not a perfect, static vault. They were a dynamic space where stars could be born, live, and die. This was the moment astronomy broke free from philosophy, setting the stage for a universe of endless possibility and change. The light of the new star was a message for all of humanity, not just the scholars of Europe. Across the globe, in the great observatories of Asia, court astronomers were also meticulously tracking the heavens. In China and Korea, these imperial sky watchers had a specific term for such an event. They called it a guest star. Their records, preserved for centuries in official histories, note the appearance of a brilliant new light in the constellation they knew as the Purple Forbidden Enclosure. The Korean royal astrologers reported it was as bright as Venus and remained visible for well over a year, a celestial visitor of immense significance. These observations were not just casual notes, they were matters of state tied to the emperor's mandate to rule in harmony with the cosmos. The supernova was seen as a potent omen, a disruption in the natural order that required careful interpretation and recording. This parallel documentation is a scientific treasure, providing independent confirmation of the event's duration and brilliance from a completely different cultural and astronomical tradition. But the phenomenon may have reached even further. Some researchers point to oral histories from Native American tribes like the Pawnee, who tell of a very bright star appearing around that time. While difficult to date with absolute precision, these stories reflect a universal human experience. From the royal courts of China to the plains of North America, human eyes turned upward in unison, captivated by the same silent mystery. This was not merely a European event that changed Western thought. It was a global spectacle, a shared moment of wonder that reminds us curiosity knows no borders and the sky is our one common heritage. That silent celestial fire did not burn only in the scientific mind. It seeped into the very soul of the culture, igniting anxieties and ambitions in equal measure. For a society deeply interwoven with religious faith, a new star was never just a star. It was a sign, a portent, a message written in light directly from the hand of God. Across Europe, pamphlets and sermons debated its meaning with a mixture of awe and dread. Was it the Star of Bethlehem returned, a herald of a second coming? Or was it a divine warning, a flare of celestial anger signaling the end of days? This cosmic uncertainty fed a profound cultural shift, chipping away at the medieval worldview where heaven was a predictable clockwork dome. The universe was suddenly alive, unpredictable, and capable of speaking in a voice of terrifying brilliance. This newfound cosmic dynamism began to appear in the art of the period, where the heavens were no longer depicted as a static, gold leaf background for saints, but as a deep, mysterious, and active space. We see it in the literature, too, where poets and playwrights grappled with a cosmos in flux, a theme that would later echo in the works of Shakespeare and John Donne, who wrote of new philosophy calling all in doubt. But this anxiety also had a productive side. The supernova created a crisis of authority. If the ancient philosophers like Aristotle could be so profoundly wrong about the fundamental nature of the heavens, then what other long-held truths were up for questioning? This was the fertile ground of doubt from which the scientific revolution would sprout. It was no longer enough to simply trust the wisdom of the ancients. The event championed a new way of knowing, one based on direct observation, on measurement, on the kind of relentless data collection that Tycho Brahe embodied. The star's light, therefore, did two things at once. It cast long, unsettling shadows of divine mystery, and it simultaneously illuminated a new path forward, one guided not by scripture or Aristotle, but by the hard, cold light of empirical evidence. It taught humanity a powerful lesson that to understand the cosmos, you must first be willing to watch it, measure it, and accept that it might just surprise you. The supernova's silence on parallax left Tycho with a monumental puzzle. If the Earth was truly racing around the Sun, as Copernicus had boldly claimed, then the nearby stars should exhibit a tiny, annual wobble as our viewing angle changed. Yet Tycho's own unparalleled instruments could detect no such shift, not even for the brilliant new star. This absence of stellar parallax was a massive, data-shaped obstacle he could not ignore. It forced him to construct a universe that could account for the new celestial dynamism while still explaining why the stars seemed so stubbornly fixed. His solution was a cosmic masterpiece of compromise, the Tychonic system. In this elegant model, all the known planets Mercury, Venus, Mars, Jupiter, and Saturn revolved around the Sun, just as Copernicus said. But then, the entire Sun-centered system itself swung in a grand, yearly circle around a motionless Earth at the very center of it all. Think of it as a celestial matryoshka doll, a solar system within a larger orbit. This hybrid geo-heliocentric model was a brilliant feat of intellectual engineering. It preserved the Earth's prized central position, which satisfied both religious doctrine and the apparent lack of stellar motion. Yet it also elegantly explained the complex planetary paths that had plagued the old Earth-centered model of Ptolemy, all while keeping the distant stars fixed and unmoving on their crystal sphere. Tycho was not merely clinging to tradition, he was trying to build a new universe from the bedrock of his own exact observations. His model became a vital stepping stone, a necessary halfway house for a world not yet ready to accept a sun-centered cosmos, but no longer able to believe in an unchanging one. It was a universe built on a contradiction, but one that perfectly reflected the transitional age in which he lived, caught between the heavens of the ancients and the universe of the future. Tycho Brahe took his most precious possession with him into exile, a treasure far greater than any silver knows. It was a lifetime of data, meticulously recorded in thousands of pages of observations. When he died in Prague in 1601, this priceless inheritance did not vanish. It passed directly into the hands of his brilliant, temperamental assistant, a man named Johannes Kepler. Kepler was a fervent Copernican, a believer in a sun-centered universe, yet he now possessed the very data that had been used to argue against it. This was the ultimate paradox. Tycho's hybrid model, the elegant compromise, would soon be rendered obsolete, but the data he collected with such obsessive care would become the bedrock of a new and lasting truth. Kepler inherited the Rudolphine tables, a massive star and planetary catalogue compiled from Tycho's work. These tables were not just a list, they were the most accurate map of the heavens ever created, a testament to the power of precision over philosophy. For years, Kepler wrestled with the orbit of Mars, a planet whose path stubbornly refused to fit the perfect circles that everyone, including Copernicus, still believed in. Tycho's data was so precise that it revealed tiny, maddening discrepancies in the Martian orbit, flaws that a lesser astronomer might have dismissed as observational error. But Kepler trusted the data. He knew that if the numbers said the orbit was not a perfect circle, then the model was wrong, not the measurements. This led him to his revolutionary first law of planetary motion, the idea that planets move in ellipses with the sun at one focus. It was a shocking break from 2,000 years of celestial perfection. Think of it this way: for centuries, philosophers believed planets moved like a car on a perfect circular track. Kepler, guided by Tycho's numbers, discovered they actually move like a child on a swing, fastest when closest to the sun and slowest when farthest away, tracing an oval path. This was only possible because Tycho's legacy was not a theory, but a mountain of unshakable facts. The Tychonic system itself was a beautiful, intricate bridge that humanity walked across only once. But the stones from which it was built, those precise measurements of star and planet positions, were used by Kepler to construct a permanent foundation for modern astronomy. The true power of observation, it turns out, is not in proving what you believe, but in having the courage to let the data tell you what is actually true. Kepler used Tycho's data to map the solar system, but the true nature of that distant explosion remained a mystery for centuries. The ghost of Tycho's star demanded a new kind of physics to be understood. We now know that brilliant flash was a specific and incredibly powerful kind of event called a Type Ia supernova. At its heart is a stellar corpse known as a white dwarf. Picture the core of a star like our Sun after it has died, a sphere of super-dense carbon and oxygen, crushed by gravity to about the size of Earth. A single teaspoon of its material would weigh as much as an elephant. This white dwarf is stable, but it has a dangerous appetite. It often exists in a binary system, orbiting a companion star. Over millions of years, the white dwarf's intense gravity begins to siphon gas away from its stellar neighbor. This stolen material piles up on the dwarf's surface, increasing its mass and the pressure in its core. Think of it as a cosmic scale with gravity constantly adding weight. There is a critical limit, a point of no return called the Chandrasekhar limit. Once the white dwarf's mass tips over this threshold, equivalent to about 1.4 times the mass of our Sun, the core can no longer support its own weight. The result is not a collapse but a runaway thermonuclear explosion. In a fraction of a second, the entire white dwarf is obliterated in a blast so uniform and so phenomenally bright that it can outshine an entire galaxy of billions of stars. This perfectly tuned detonation is what makes Type Ia supernova so precious to astronomers. Because every single one ignites at almost the exact same mass, they all reach nearly the same peak brightness. This makes them what scientists call standard candles. Imagine you are in a vast, dark field and you see two identical light bulbs. If one appears much dimmer than the other, you instantly know it must be farther away. Type Ia supernova are the universe's perfect light bulbs. By observing how bright they appear from Earth, astronomers can calculate their distance with incredible precision. It was this very property that would allow the ghost of Tycho's star centuries later to help uncover the universe's most shocking secret. That cosmic detonation did not simply fade into darkness. Its echo is still visible today, a ghostly cloud of gas and dust expanding at millions of miles per hour. This is Tycho's supernova remnant, a cosmic crime scene we are still investigating 4 centuries later. Through the eyes of space telescopes like Chandra, which sees the universe in X-ray light, this remnant is transformed from a faint smudge into a breathtakingly intricate structure. We see a delicate, bubble-like sphere of incandescent gas, rippled with violent shock waves that appear as brilliant blue and green filaments. These are the outer edges of the blast wave, the leading front of the explosion as it plows into the cold, thin gas of interstellar space. But the true forensic evidence lies deeper within. At the remnant's heart, data reveals a shell of silicon and iron, the unmistakable ash forged in the heart of that titanic explosion. These are the elements that were created in a single, catastrophic instant when the white dwarf was torn apart. Every color in these stunning images tells a part of the story, a chemical fingerprint of the stellar bomb that detonated in 1572. It is a celestial recycling plant in action, scattering the raw materials for new stars, planets, and even life itself across the galaxy. The case is not yet closed. Astronomers are still piecing together the exact trigger, searching for the companion star that donated its mass to the white dwarf, and studying how such a perfectly symmetrical explosion could create such a complex and beautiful wreck. The light we saw may be long gone, but the evidence it left behind continues to speak, telling us the story of its violent birth and the new beginnings it scattered across the cosmos. 4 centuries after the explosion, the cosmic detective work is far from over. One crucial piece of evidence remains stubbornly absent: the star that triggered the catastrophe. In every Type Ia supernova, there must be a donor, the companion star whose mass was stolen by the white dwarf. For Tycho's supernova, finding this stellar accomplice has become one of astronomy's most compelling cold cases. Using the Hubble Space Telescope, scientists have scanned the heart of the remnant with the precision of a forensic team. They are looking for a star that seems out of place, one moving at an unusual speed or showing the chemical scars of a nearby nuclear blast. The investigation has turned up several promising suspects. One leading candidate is a tiny, dim star known as Tycho G. It appears to be moving away from the blast's epicenter faster than its neighbors, as if it was given a powerful kick by the explosion. The other main suspect is a more typical Sun-like star. The debate hinges on interpreting the evidence. Could Tycho G's motion just be a coincidence? Does the other star show the right chemical signatures of contamination from the blast? Each candidate fits part of the profile, but neither is a perfect match. This is not just an academic puzzle. Identifying the companion tells us exactly how these standard candle explosions ignite. Was it a slow, steady siphon from a normal star or a violent merger between two white dwarfs? The answer defines the very tool we use to measure the cosmos. The hunt continues, a reminder that even the most brilliant cosmic events leave behind subtle clues, waiting for the right moment and the right tool to reveal the final truth. The expanding cloud of Tycho's star is more than a beautiful relic. It is a celestial treasury of newly forged elements. When astronomers point their most powerful telescopes at this remnant, they do not just see light, they read a chemical story written across space. Using a technique called spectroscopy, they break the light from the remnant into a rainbow of colors, a spectrum that acts like a unique barcode for every element present. Each element, when heated, emits light at specific, unchangeable wavelengths. It is a cosmic fingerprint. In the light from Tycho's remnant, the fingerprints are unmistakable. They reveal strong, clear signals of silicon, sulfur, and most importantly, vast amounts of iron. This is the smoking gun. These are not elements that were simply floating in space. They are the specific ashes predicted by the thermonuclear furnace of a Type I supernova. In that single, catastrophic detonation of a white dwarf, temperatures and pressures soared to unimaginable levels, fusing lighter elements into heavier ones in a runaway chain reaction. The silicon and sulfur were created in the outer layers of the blast, while the iron, the final, stable product of nuclear fusion, was forged in its white-hot heart. This iron is the very same element that courses through your veins, a vital component of the hemoglobin that carries oxygen in your blood. The silicon is the fundamental building block of rocky planets like Earth, the sand on a beach, and the core of the world beneath your feet. Every time you feel your pulse, you are feeling a rhythm powered by a star that died centuries ago. Every stone you walk upon is made of cosmic debris. We are not just observers of the universe, we are literally made from its most violent and creative events. The remnants of that explosion are not just out there, they are right here, a part of us and the ground we stand on. That expanding shell of incandescent gas is far more than a simple cloud. It is a titanic shock wave, a cosmic tsunami racing through the galaxy at thousands of miles every second. As this immense wall of energy plows into the thin, cold gas that drifts between the stars, it superheats the material to millions of degrees, causing it to glow in the fierce X-ray light that our telescopes now capture. This process creates the beautiful, delicate bubble we see, but the real action is invisible to our eyes. The shock wave is also the most powerful natural particle accelerator in the universe. It acts like a colossal magnetic slingshot, grabbing stray atomic particles, mostly protons and electrons, and flinging them forward with unimaginable force. These particles get caught in the turbulent magnetic fields at the shock front, ricocheting back and forth, gaining a tremendous speed boost with each pass until they are hurled out into the depths of space, traveling at nearly the speed of light. We know these particles by another name, cosmic rays. They are the silent, invisible rain that constantly bombards our planet, passing through your body right now as you listen. Every second, hundreds of these subatomic bullets, born in cataclysms like Tycho's Supernova, zip through you and everything around you, utterly harmless but carrying the direct energy signature of a stellar explosion. By studying the shock wave in Tycho's remnant, scientists are essentially studying a giant, natural laboratory for high-energy physics. They can observe how particles are accelerated to such incredible energies, a process we struggle to replicate even in our largest machines on Earth. This helps us understand not just supernova, but the most violent and energetic events across the cosmos, from the jets of black holes to the hearts of distant quasars. The ghost of that star is still teaching us, showing us how the universe builds its most powerful engines from the ashes of its own destruction. The original flash of light from 1572 is long gone, but its ghost still travels through space. Modern astronomers have captured this ghost not from the remnant itself, but from its reflection. They call this phenomenon a light echo. Imagine shouting into a vast, empty canyon. The sound waves travel out, hit the distant canyon walls, and a moment later, the echo returns to your ears. Light behaves in a similar way, though on a vastly grander scale. When Tycho's star exploded, its light radiated outward in all directions at, of course, the speed of light. The first wave of this light traveled directly to Earth, arriving in 1572 and stunning observers like Tycho. But some of that light did not come straight to us. It continued traveling into deep space until it encountered vast, dark clouds of interstellar dust. These cosmic clouds acted like the canyon wall, reflecting a tiny fraction of that ancient light. Centuries later, that reflected echo finally curved around and arrived at our telescopes. This means the light that Tycho Brahe saw with his naked eye has been literally bouncing around the galaxy, and we can now catch it with our most sensitive instruments. It is a message from the past, a photon that has been in flight since the 16th century, finally delivering its secrets. By analyzing the spectrum of this echo, scientists performed the ultimate cold case analysis. They took the very light from the original event and broke it down into its constituent colors, reading its chemical fingerprint. The spectrum revealed the unmistakable signatures of silicon and iron, the definitive proof that the supernova was indeed a type Ia. This was not an inference from the remnant's current state. It was a direct analysis of the explosion's light itself. We are no longer just studying the aftermath. We are replaying the original event, confirming across a gulf of 4 centuries what Tycho could only marvel at. The universe provided its own perfect recording, a celestial echo that allowed us to look over Tycho's shoulder and finally understand what he was truly seeing on that cold November night. Every astronomer's greatest challenge is measuring the impossible vastness of space. How do you calculate the distance to a faraway galaxy when you cannot simply stretch a cosmic tape measure across the void? The answer was found in the ashes of explosions like Tycho's. Type Ia supernova became the universe's ultimate measuring tape, a tool known as a standard candle. Think of it like this: if you see 2 identical light bulbs in the dark, and one appears 100 times dimmer than the other, you instantly know the dimmer bulb is 10 times farther away. The physics is beautifully simple. Because every type Ia supernova ignites at that same critical mass, they all detonate with nearly the exact same intrinsic brightness. They are nature's perfect light bulbs. Astronomers know their true wattage, so when they spot one of these supernova in a distant galaxy, they simply measure how dim it appears from Earth. The difference between its known true brightness and its apparent observed brightness gives a direct, precise calculation of its distance. This single property transformed our ability to map the cosmos. It allowed these stellar explosions to become the most crucial rung on the cosmic distance ladder, the method we use to leap from measuring nearby stars all the way to the edge of the observable universe. It was this reliable, predictable dimming that astronomers in the 1990s relied on for a monumental project. They searched for distant type Ia supernova, expecting to see how the expansion of the universe, the aftermath of the Big Bang, was gradually slowing down over time due to the pull of gravity. They pointed their telescopes deep into space, collecting light that had been traveling for billions of years, and they measured the dimness of these standard candles with meticulous care. The data revealed something that defied all expectation. The distant supernova were not just far away, they were too far away. They were dimmer than they should have been if the universe's expansion was merely coasting or slowing. The only possible explanation was that the expansion of the universe is not slowing down at all. It is speeding up. Some mysterious, repulsive force, now called dark energy, is stretching the very fabric of space itself, pushing galaxies apart at an ever-increasing rate. This stunning discovery, which earned a Nobel Prize, means that the ghost of Tycho's star did more than just shatter an ancient idea of the heavens. 4 centuries later, It helped us uncover the greatest cosmic mystery of our time, a force that dominates the fate of the entire universe. That meticulous map Tycho Brahe created with brass and patience has just passed the ultimate test, a comparison with the universe's most powerful supercomputers. Modern astrophysicists can now simulate the entire life of Tycho's supernova remnant, modeling the physics of the blast wave as it expands for 450 years. When they run these digital recreations, they need a starting point, an initial set of conditions to set the virtual explosion in motion. The most critical piece of data is the exact location of the blast's epicenter. Where do they get this foundational coordinate? They turn directly to the positions Tycho Brahe recorded by hand in 1572. The result is nothing short of breathtaking. The simulated remnant, born from equations and processing power, expands to a size and shape that aligns almost perfectly with the actual cloud of gas we photograph today with the Chandra X-ray Observatory. The center of the modern remnant matches the position Tycho measured to within a tiny fraction of a degree. Think about the chain of validation this represents. A man looking through a sighting tool on a cold Danish island without a single lens or electronic aid produced data so clean and precise that it can be plugged directly into a 21st century supercomputer to accurately predict the state of a cosmic object 4.5 centuries into his future. His numbers are not a historical curiosity, they are active, functioning inputs in our most advanced models of stellar death. This is the ultimate legacy of empirical science. It builds bridges across time. Tycho's belief that the heavens could be understood through measurement alone created a data point so durable that it now helps calibrate our understanding of the universe itself, proving that true accuracy is timeless. The silent flash that terrified Renaissance Europe now fuels the blockbuster dreams of our own era. We have taken the raw cosmic power of a supernova and woven it into the very fabric of our stories, transforming a scientific phenomenon into a universal symbol. In science fiction, a supernova is rarely just an explosion, it is a narrative engine. It becomes the ultimate power source for a hyperdrive, the cataclysm that forces a civilization to flee its home world, or the apocalyptic weapon of a star-faring empire. This is the legacy of Tycho's star, translated through centuries of discovery into a language of wonder and dread we can all understand. When a starship captain in a film orders a jump to light speed, the energy often visualized as a brilliant, star-like burst, it is the ghost of that supernova providing the thrust. The entire plot of a major video game can hinge on escaping a system before its sun goes supernova, turning a cosmic event into a race against time that any player can feel in their gut. These stories work because they tap into a primal human understanding, one that Tycho himself helped to forge, that the universe is both beautiful and violently alive. The supernova symbolizes rebirth as much as destruction. It is the cosmic furnace that forges the elements for new planets and new life, a cycle of death and renewal on the grandest possible scale. So the next time you see a star explode on a movie screen, remember you are witnessing a 400-year-old conversation, a direct line from Tycho Brahe's metal nose and brass quadrants to our own endless fascination with the power that shapes the cosmos. That expanding bubble of incandescent gas is far from finished with its work. The story of Tycho's star will continue to unfold for tens of thousands of years, a slow-motion drama written across light years of space. For millennia to come, the remnant will keep expanding, its shock wave plowing through the thin hydrogen gas of interstellar space. As it grows, the sphere of hot gas will become larger, thinner, and inevitably cooler. The fierce X-ray glow captured by our telescopes today will gradually fade, shifting first into visible light and then into the dimmer infrared. The beautiful, intricate structures we now see will soften and disperse, like a puff of smoke slowly dissolving into a vast, dark room. The remnant's ultimate fate is to become invisible, a cold, dark cloud of gas drifting silently between the stars, But this is not an end, it is a transformation. The iron from the explosion's heart and the silicon from its outer layers, the very elements we identified as its chemical fingerprint, will not be lost. This enriched material, this cosmic ash, will eventually mix with the surrounding interstellar medium. Imagine the galaxy as a great ocean, and this cloud of supernova debris is a nutrient-rich current, spreading the essential ingredients for new worlds. Millions of years from now, a random trigger, perhaps the shock wave from another dying star, will cause a pocket of this mixed gas to collapse under its own gravity. In that new stellar nursery, the iron from Tycho's star could become part of a rocky planet orbiting a newborn sun. The silicon might form the very continents of that world. The cycle of stellar death and rebirth is the engine of our galaxy's evolution. We exist because generations of stars lived and died before our sun was even a glimmer in a nebula. The final legacy of that brilliant flash in 1572 is not a fading cloud, but the promise of future suns and the potential for new life, built from the very atoms of its ancient destruction. The possibility of another star erupting into naked-eye brilliance is not a matter of if, but when. Our own Milky Way galaxy hosts several stellar time bombs ticking quietly in the darkness. The red supergiant Betelgeuse, the fiery shoulder of Orion, is a prime candidate. This colossal star is a cosmic heavyweight in its final act, and a supernova explosion is its inevitable fate. When it finally goes, it will not be a subtle event. For a few glorious weeks, it could outshine the full moon, casting sharp shadows at night and visible alongside the sun in the daytime sky. Another potential candidate is the Tycho system, a binary pair of stars much closer to the solar system. Here, a white dwarf is already siphoning material from its companion, inching toward that same catastrophic limit that destroyed Tycho's star. The timeline for these events, however, is measured in cosmic deep time. Betelgeuse could explode tomorrow, or it might not detonate for another 100,000 years. The universe operates on a schedule far beyond human concern. For astronomers, the sudden appearance of a new, brilliant star would be the scientific opportunity of a millennium. It would be a front-row seat to stellar death, a chance to observe the entire life cycle of a supernova in real time, from the first neutrino burst to the unfolding of the remnant, with every tool of modern science at our disposal. And what of the danger to Earth? The reassuring truth is that any star close enough to go supernova and truly threaten our planet with harmful radiation is already on a very short, well-monitored list. Both Betelgeuse and Tycho are comfortably outside this lethal radius. The radiation would be largely absorbed by our atmosphere, resulting in a spectacular light show and a bonanza for science, but no existential threat. The legacy of Tycho's star assures us of this, a cosmic drama of creation and destruction where we are the privileged and perfectly safe audience. That single point of light did more than illuminate the sky, it illuminated a new way of thinking. The Tycho Supernova was a cornerstone of the scientific revolution, not merely because it was observed, but because of how it was observed. It marked the pivotal moment when empirical evidence, gathered through relentless measurement, began to dethrone philosophical dogma as the ultimate source of truth. Before this event, the universe was understood through the lens of ancient authorities. Afterward, it was understood through data. Tycho Brahe's meticulous charts were the bridge. He provided the raw, unassailable numbers that proved the heavens were not perfect and unchanging. This created the intellectual space for the giants who followed. Johannes Kepler used Tycho's own data to shatter the last vestiges of celestial perfection, proving planets move in ellipses, not perfect circles. Galileo Galilei, turning his telescope to the heavens, found moons orbiting Jupiter and imperfections on the Sun, further demolishing the Aristotelian cosmos. These discoveries were only possible because Tycho had already broken the spell. He normalized the idea that the cosmos could be measured, quantified, and understood on its own terms, even when those terms contradicted 2,000 years of belief. This shift in methodology culminated in the work of Isaac Newton, who could not have derived his universal law of gravitation without the precise planetary data that traced its origins back to that initial explosion. The true legacy of the supernova was this fundamental change in humanity's relationship with the cosmos. We were no longer passive subjects of a mysterious, perfect realm. We became active investigators of a dynamic, physical universe governed by laws we could discover. The star's light faded, but the new light it sparked in the human mind has only grown brighter, empowering us to ask not what the universe should be, but to measure what it actually is. You can still stand in the very spot Tycho Brahe did, looking up at the same patch of sky. To find the ghost of his supernova, first locate the constellation Cassiopeia, that distinct W or M shape circling the North Star. The remnant lies almost exactly in the center of that celestial letter, a faint cloud-like smudge invisible to the naked eye but waiting for your camera. The ideal time to search is on a crisp, moonless autumn night when Cassiopeia rides high in the sky from evening until dawn. This is your window into the past, a direct line of sight to a cosmic crime scene. While your backyard telescope will not reveal the intricate shock waves, a simple pair of binoculars from a dark sky site can show you the star field where history was made, the same pinpoints of light Tycho used as his fixed reference points. To truly capture the remnant's faint glow, you will need to embrace the art of astrophotography. This is where the hobby becomes a hunt. Start with a DSLR camera, a sturdy tripod, and a wide field lens. The technique is not about a single snapshot, but about patience and stacking. You take hundreds of individual long exposure images, each one collecting precious photons that have traveled for centuries. Specialized software then combines all these frames, averaging out the digital noise and amplifying the incredibly faint signal of the nebula itself. For the ultimate challenge, narrowband filters that isolate the specific light of hydrogen and oxygen gas can be used with a tracked telescope to unveil the remnant's delicate bubble structure. The result is more than just a picture. It is your own personal record of a 450-year-old event, a testament to the fact that the cosmos is not a distant abstraction. It is a place you can visit, a story you can capture with your own hands, connecting your curiosity directly to the legacy of an astronomer who once stood under the same stars, asking the very same questions. 4 centuries after the flash faded, the case file on Tycho's star remains stubbornly open. Scientists are still piecing together the final moments of this cosmic detonation, and the biggest questions demand answers that the data has not yet surrendered. The identity of the stellar accomplice is perhaps the most famous cold case in astronomy. Was the white dwarf fueled by a slow, steady siphon from a sun-like star, or did it gorge itself in a violent merger with another white dwarf? Each scenario leaves a different chemical fingerprint and a different kind of survivor, and the hunt for that companion star continues with every new observational run of the Hubble and James Webb Space Telescopes. Then there is the explosion itself. The physics of the flame that rips through a white dwarf is devilishly complex. How does a subsonic flame of nuclear fusion suddenly transition into a supersonic detonation wave that consumes the entire star in a heartbeat? Supercomputer models can simulate this, but subtle differences in the initial conditions create vastly different outcomes in the elemental ash that is scattered into space. This leads directly to the final great mystery, the precise recipe of its chemical enrichment. The remnant is a cloud of cosmic ingredients, but were they mixed perfectly? The distribution of iron, silicon, and radioactive nickel we observe tells a story about the explosion's symmetry and power, a story we are still learning to read. Every new observation adds another piece to this 450-year-old puzzle, reminding us that the universe reveals its secrets slowly, one patient measurement at a time. The final chapter on Tycho's supernova has not yet been written, and the next great discovery could be just one telescope image away. From a single point of light in 1572 to a fundamental key for unlocking the cosmos, the journey of Tycho's star is a testament to human curiosity. It began as a silent shock to a philosophical system, observed with brass instruments on a Danish island, and has now evolved into a standard candle measuring the accelerating fate of the entire universe. This story connects a man with a metal nose to our modern hunt for dark energy, proving that one observation can ripple across centuries. The next time you find yourself under a clear night sky, look for the familiar W of Cassiopeia. Knowing that within its bounds lies a cosmic ghost, a remnant of an explosion that rewrote our place in the universe, might just change how you see the stars forever. They are not just distant lights, but active, dynamic, and deeply connected to our own existence. We would love to hear what part of this cosmic story resonated most with you. Share your thoughts in the comments below, and if you enjoyed this journey from the past to the future of science, subscribe for more adventures that explore the cutting edge of technology and the lifestyle it creates.